Now, some of these infinite limits are not in indeterminate form, and some simply require an observation. Now, as x increases with that bound, this innermost expression increased that bound. But when the input of the inverse tangent function increased that bound, the corresponding outputs go to this. Of course, there's a horizontal asymptote in the right-hand plane on the graph of y equals inverse tangent of x. And there it is, y equals that value. If I change this to that, of course, in the left-hand plane, that's the behavior. Now here, I'm left with this increase that bound, this increase that bound. I'm looking at their difference. And it doesn't work. It doesn't work for this reason. I applied erroneously one of our basic limit laws. The limit of difference is a difference in individual limits, but the individual limits did not evaluate to a finite fixed real number, so that particular limit property does not apply. So I'm going to panic and play around with the expression with the limit, see what I can come up with. Now take a peek at that. Since this increased that bound as well as the second factor, then certainly the product is going to increase that bound as well. Here, just like my first question, as x increase that bound, so does this, so does that. But if the input of the natural log increase that bound, then the natural log is going to increase that bound. But that's now the input of the hyperbolic tangent function. And as the input of the hyperbolic tangent function increase that bound, the corresponding outputs go to 1, only because we're so familiar with hyperbolic functions. Okay, maybe that too was a bit of waste of your time. Let me get more sophisticated. My last example, finally getting to love the sophistication of it. Notice how if I squint my eyes, got the single term upstairs, which is this. But only looking at the leading term downstairs, that would be radical that. But the square root of x squared is just x for positive values of x. I'm getting that linear kind of expression over something that's basically acting as a linear expression downstairs in terms of highest powers. Notice I also have multiple terms downstairs, one of which involves a radical. So here's my approach to dividing this limit. If I only look at this one term, it involves the square root of x squared, which is just x. If x is positive, then it is. And since that's the highest power downstairs, namely 1, then I'm going to multiply top and bottom by 1 over x to that power. Now, I'm not liking what I see in the sense that technically speaking, I can't bring this 1 over x underneath the radical, unless I can rewrite that as a radical expression, but I can. Now I need to rely on my memory. Now, it is the case that these 3 go to 0 as x increases that bound. So I am merely left with this. Now, if you allow me to just put one small twist on this, so you ready? Let's see what happens as x decreases that bound. I like it. I like it. I don't like it. And technically speaking, eventually x is going to be negative, meaning this factor right here in the second term downstairs is understood to be negative. But if you take a peek at this expression, it's equivalent to it, but with a sign change, because when x is negative, this is positive. Since this factor is negative, but it transformed to a positive one, which I did not want to happen, I will fix the clumsy mistake. Now that fixes that this fact here is indeed equal to that for negative values of x. But in the end, that changes my answer. What it really means is this. On the graph of this equation, in the right-hand plane, I have a horizontal asymptote. In the left-hand plane, I have a horizontal asymptote, but they're not the same.